Professor Gordon Savage was born in Canada and received his PhD from the University of Waterloo in 1977 in the area of graph-theoretic models of engineering systems. He is presently a faculty member of and a full professor in the Department of Systems Design Engineering at the University of Waterloo, Ontario, Canada. His present research interests are in the areas of modeling, formulation and computer implementation of linear graph models of engineering systems, and the design for quality, reliability and robustness in complex engineering systems. He has published over 90 refereed papers, and the focus of his ongoing research is to integrate quality and reliability metrics using both mechanistic and empirical models. He has been involved in the study of methodology of design for over 30 years and spent parts of 7 years presenting the process of innovation in China. His practical experience in industry and his supervision of the Midnight Solar Car project give him a unique ability to link the methodology of design, the process of innovation, and robust design. He will be conferred the Lifetime Achievement Award of the Systems Society of India in its forthcoming National Systems Conference, NSC 2010 at NIT Surathkal. Professor Savage.
Good morning. So the talk will be on the graph-theoretic field model for spatial continue, and this is some work that I did fairly a large number of years ago now. So we'll see what we can learn from this. So the motivation for this talk actually came from an abstract by, I guess it was the abstract by the previous paper.
And the outline of the talk will be, first of all, I'll look at models of physical systems based on graph theory, and that will kind of give the foundations for the main work I want to present on the graph-theoretic field model. What's interesting is that the second talk will be the theory of multi-terminal representations, and you'll see an interesting application of that as we go on into the talk. And then we'll come to applying the graph theory to field and continuum problems. And after that, we'll look at some applications and show that the graph-theoretic field model does have some very interesting fundamentals to it.
So looking at models of physical systems essentially from a graph-theoretic basis, we see that there are only two types of measurements, and sometimes you mix up the term measurements and variables, and they would be the through measurement, and the typical ones from kind of, I guess, mechanistic models would be current and force and fluid flow and even heat flow. And we saw some further ones earlier today. Cross measurements, they're fairly classical too. We have the voltage in electrical, velocity in mechanics, pressure in fluids, and temperature in thermodynamic and thermal problems. And they're quite interesting. The next important feature is that every model has two parts. Models of components, and that's really what we mean by a system. It's an interconnection of components, given some excitations, and we get some response. And then we get the models of the pattern interconnection. There are only so many types of components, and they typically fall under the following 6 classes. The sources or loads, where we can fix some of the measurements as desired. The dissipative, where energy is being released as heat. Storage, where we're either saving energy or releasing energy. Transformers, which typically in a particular process move energy from one part of the process to another part. And the well-known applications would be gears in rotational mechanical, where we're trading off torque for angular speed. And then there's the good old lever, where we're trading off displacement or length for force. The transducer, it's the common component for moving energy from one discipline or process to another process. So the electrical DC motor is an example of that. We're moving energy from the electrical domain into the rotational mechanical domain. And also we can add in the amplifier, where we're bringing in energy from the environment and putting it into the system or taking it out as required. So in terms of the component models, there's the group we have to work with. In terms of the interconnection model, we have two rules. The vertex postulate, which constrains the through measurements or through variables, and the circuit postulate, which will constrain the across measurements. And it all sounds pretty simple, and it should, that's the kind of the beauty of the graph-theoretic field model. It starts with this and moves on. And to see how we go from the general idea of a system to graph theory, let's look at the nature of a complementary pair of measurements and then the abstract representation. What we first do is pick two terminals, usually with respect to a component. So in this case, we can pick A and B. And then the across measurement is made in parallel with the terminals, component body, and well, the first terminal, component body, and the other terminal. So A, component body, and B in parallel. The through measurement is made in series with the two terminals and the body, as we can see in the diagram. So there's X, Y in parallel, and there's Y1, the through meter in series. Now, to get into an abstract symbol, so we can look at any system we wish, we can replace the terminals with nodes, the circles, and looking at the polarity of the measurements, which in this case we've tried to get to agree to be either both positive or both negative, we can represent them by an oriented line segment, sometimes called an edge. And then we just put a number on the edge, and that represents the complementary pair of measurements. This symbol, of course, is called the terminal graph, in the sense that it measures the measurements are made with respect to terminals. The component model has a postulate, and I guess I can read it off here. And it says that an n-terminal P process, so P processes, two processes, be say electrical, mechanical, can be completely characterized by n minus P complementary pairs of measurements represented by a terminal graph that has the topology of a forest or a tree in each part. And that's saying a little more than we need to say. If we look at the example and just look at the yellow, the process, we'll call this process 1. It has two terminals, and therefore we can just say n minus 1 for that, which would be 1, and there's the terminal graph. For the second, or the blue process, let it have the single process, have 3 terminals, and 3 minus 1 is 2, and there's the pair of complementary measurements, in this case formed as a tree. For each of the edges in the terminal graph, we require equations. So in this case, we have 3 edges in the terminal graph. We need 3 equations. It's very simple. And these equations are written in terms of the complementary measurements or variables for each of the 2 processes. So there we have 3, and there's our 3 equations. So 1 equation for each edge. Now, the interconnection model, it's interesting. So we look at 2 pieces here. The system graph arises from the interconnection of the terminal graphs at the nodes corresponding to the interconnection of the components at the terminals. And so a little example here, we have a number of components. C1 has 2 terminals, B and E, and there's its terminal graph. C2, 2 terminals, there's its terminal graph, B to C. Same for 3, and 4 and 5, 3 terminals, so it has the terminal graph with 2 edges, 4 and 5. Now, this time maybe we could talk a little bit of graph theory, since this is now the system graph, and it's just an example of an oriented linear graph. And in terms of some of the graph theory, we can talk about paths, which is a set of edges starting at a particular node and ending up at another node. So going from B to C, the path would be 4 and 5. Another subgraph of interest are circuits, and basically we start on a particular node and go around in a loop. So we can talk about a circuit as a subgraph 4, 5, and 2. And the simplest circuit would be just 2 edges, say 5 and 3. We can also talk about a subgraph called a cut set, and the cut set is a set of edges when removed divides the graph into two parts, or in a simple sense segregates the nodes into two distinct sets. So if we take out 2, 5, and 3, for example, then we leave node C and another part with nodes B and C. And another example, we could cut through 1, 4, 5, and 3. If we take those out, we leave E, and instead of nodes at the top, B and C. If another graph is called the tree, and it's a subgraph that joins has a path between all the nodes, but has no circuits. So a tree could be the edges 1 and 2, and they're indicated in bold. The edges in, and this is interesting, but the edges in the tree are called branches, makes sense, and the edges in the co-tree are called chords. And so graph theory is quite an interesting area, especially in some of the naming. Once we introduce the idea of a tree, the remaining edges are the chords called the co-tree. Now we talked about cut sets and circuits. We can talk about fundamental cut sets. A fundamental cut set has one branch and some chords. So there's a fundamental cut set. There are 2. There's the branch, 5 and 3. And the other fundamental cut set would be 1, 4, 5, and 3. In the same sense that we can talk about fundamental cut sets, we can talk about fundamental circuits. So it has one chord and some branches. So we have 5, 1, and 2 represents a fundamental circuit. Now, in terms of the equations, it's interesting. So we come down to the interconnection equations. Let's talk about the vertex postulate. It simply says that the oriented sum of the through measurements implied by the edges in a given cut set is 0 at any instant of time. So, looking at what we mean by this orientation, if we look at fundamental cut set 2, which has 2 chords 5 and 3, if we let the branch be the defining orientation, C is the reference, so we see this could be Y2, and 5 opposes, so that would be minus Y5, Y3 opposes or is out, so that would be minus Y3. So we have Y2 minus Y5 minus Y3 is equal to 0 at any instant of time. The other fundamental cut set involves branch 1, and it would cut with the other chords 4, 5, and 3. And again, we can form the cut set equation by looking at the notation here. Using E as the reference, we have Y1 plus Y4 plus Y5 plus Y3 is equal to 0, since they all have agreed with the orientation of the branch. So we can write these cut set equations in a matrix form, and if we pull out the vector Y, the through measurements, we get the fundamental cut set matrix. And in essence, these are called fundamental cut set equations for a very simple reason. The fundamental cut sets have one branch, and one branch only. There's only so many of those. Any other cut set has more than 2 branches, so there would be a non-fundamental cut set which contains 1, 4, and 2. It's got 2 branches in it. Well, it turns out that once you have the fundamental cut sets, any other cut set is just a linear combination of the fundamental. So the fundamental cut sets form the basis. That's all the information there is in terms of the vertex postulate. The same look at the circuit postulate over here. The oriented sum of the cross measurements implied by the edges in a given circuit is 0 at any time. So for each of the chords, we can form a fundamental circuit. So there's 4 with 1. So in this case, what we could do is looking at letting 4 set the orientation. So this would be, say, X4. And this opposes the direction, so this is minus x1. So we have x4 minus x1 is equal to 0. And we do the same for 5. We go around. 1 opposes, 2 agrees, so we can put the plus and minus for the cross measurements in, the same for 3, and so we end up with 3. We put these in a set of equations and put them in matrix form. We bring out the cross measurements x. We get the so-called fundamental circuit matrix. And it's fundamental in the sense that any other circuit will have two chords, and that's a linear combination of the fundamental ones. So all the interconnection equations is contained neatly in the fundamental cut set equations and the fundamental circuit equations. There isn't any more interconnection information then. Now, in the material I'm going to address later, another set of topological equations will come out, and they're called the vertex equations. And these equations, all we do is look at any node and form what they call a nodal cut set. So a nodal cut set for B would be 1, 4, and 2, and usually the orientation is such that incident away is plus and incident towards is negative. So in this case, they're all incident away. If we could do 1 for C, in this case, we would have minus y2 plus y5 plus y3 is equal to 0. And that's the nature of that. And these also build up into the same number of equations, n minus p. So in this case, for cut sets, we're going to get 2 for 1 and 2, and for the vertex equations, we're also going to get, we can get 1 for B and for C, or for C and E, and so on. We just need 2. They're not as elegant, but we'll see that they're easy to form, and will be applicable later. The matrix here is called the incidence matrix, and it just gives some of the topological information on the graph. Another set of equations which are in nature of the circuit postulate are the nodal transformation equations. In this case, we introduce some extra cross measurements in the following senses. We pick a reference, and then we make extra measurements, across measurements, in this case B to E, for example, and C to E. Then all of the across measurements in the graph can be made as combinations of these nodal across measurements. And it turns out that the relationship can be written as the transpose of the incidence matrix. We add some information, but we get a very simple result. Now, there's a little, as we saw in the previous speaker, there's a little more information which we can pull out of our hat here in graph theoretic models. And that is the following. The vertex postulate and the circuit postulate imply the principle of orthogonality that has units of power or quasi-power. Note only 2 relations are necessary. Now, what we're saying is that if we postulate the vertex postulate, and we get a set of through variables that satisfy this relationship, and in the cross instance over here, in the circuit postulate, we get a set of across measurements that satisfy this relationship. Then we automatically have that the vector of the cross measurements times transpose times the vector of the through measurements is equal to 0 at any instant of time. In other words, this is just the scalar product, and this is also the so-called system power. So the system power, or quasi-power, depending upon the units, if that's 0 at any instant of time, integrate the system power over time. We get units of energy, and so what it says then is that looking at 2 times T1 and T2 is that the change in energy is equal to 0. So in other words, the vertex postulate and the circuit postulate imply conservation of energy. Amazing. And it turns out that we can pick any two of these relationships and use them as an interconnection model. So we can pick the principle of orthogonality and the circuit equation, and we'll see that this will give us the fundamental cut set equations. Now, another thing that's interesting about this principle of orthogonality is that you can pick a set of through measurements at some instant of time, say T1, and you can pick the set of across measurements some other time, say T2. And because they're only topologically related, the scalar product will still remain 0. In fact, if you have 2 systems with the same graph, so they're topologically similar, you can take the set of through measurements from one system and the set of cross measurements from another system. So this might be currents and this might be pressures. And again, you'll see that the scalar product of those 2 vectors will be 0, just because it's a topological phenomena. And it goes back to the fundamental cut-set matrix and the fundamental circuit matrix. It's one of the amazing things about these linear graph theory models. System equations, again, we need the 3 sets of equations. So we have a system graph with E edges and we have 2 E measurements. And lo and behold, what do we get? We get E component equations. Remember I said that the postulate was we get 1 equation for each of the edges in the terminal graph. We get N minus P fundamental cut set equations, and then we get what's left over, the fundamental circuit equation, and add them all up, and what do you get? So we've got all the information there is in the system. So these equations, that's it. Now, something else which is important we'll talk about later is this idea of formulations, and this is the substitutions of the system equation. And to get a smaller, more interesting or more useful set. So we can start with the fundamental cut set equation, substitute the component equation, substitute part of the fundamental circuit equations, and we get down to a smaller set of equations. That's what we mean by formulations. Now, this, you'll see how I apply this later on, this multi-terminal representation theory. And the original need for the approach was they were trying, well, I guess it was I was before me, they were trying to solve a large problem through the sum of a number of small problems. So if we look at this representation here, we see, say, 3 repeated subsystems. Each subsystem has the same internal structure. And the idea is fairly simple, is let's pull out one of the subsystems. And this is conceptually, of course. You pull it out, and you look at it. We have terminals of interconnection A, B, C, and D in this case. So we have 4. So going back to the component postulate, what do we need? Well, we need a terminal graph that has 4 minus 1 process, edges in the terminal graph. Well, there it is over there, for example. Now, next thing we can do is let's use the internal structure to see if we can get information at excitation. So we'll put on some excitations, and these are like sources, and we'll put them on with the same topology as the system graph we chose. So if we can go back, we can see we had 1 was A to D, and B was 2 to D, and what did we choose? Sure enough, there's 1. There's excitation 1, 2, and 3 in the same topology as the system, the terminal graph for the multi-terminal representation. Now, let's look at how we get the equations here. And this is a little redundant, but it's in a form that I want to use later. So what we'll do is we'll look at the principle of orthogonality for the excitations and the internal structure, and also the excitations on the multi-terminal representation. So when we move information from left side to the right side, we have the total sum, then we change the sign. So what we can see here is there's the principle of orthogonality for excitations and the multi-terminal representation, and there's the principle of orthogonality for the excitations and the substructure. And what we're interested in is, of course, this relationship here, and the minus sign disappears. So what I want to do then is try and get a relationship between y and this x here. So what we'll do then is use the internal structure, and the way I'm going to do this is a little clunky. We wouldn't normally use this, but I say it's going to be to my advantage. So we'll substitute the terminal equations, and I've left to put a bit of source on here. Use this nodal transformation, so we bring in these set of nodal cross values, and then we start getting this nice product in here. So we just keep this guy on the side, and these substitutions give us this little piece here, and this will be more for like the conductances, and this is for the sources. Now, I'm kind of cheating here a little bit, and we will solve out the internal structure, and I get a relationship between all these nodal measurements and basically the excitations, which are the multi-terminal cross variables. If we substitute this in, we get this long matrix multiplication in both terms here. But this term in the middle here is important. We'll call that G. and that takes care of the conductance properties of the subsystem. And here we have N transpose A, et cetera, takes care of the sources. Now, since on both sides we have this X transpose sitting out in front, and it's arbitrary anyhow, so we pull that out, and lo and behold, to make sure this identity works, we must have Y is equal to GX plus any source information. I'll come back to this in a little bit and show you how we use this. But again, there's the use of this principle of orthogonality. Now let's look at the field problem for the second half of this talk. And the problem is, well, in a nutshell, there aren't any components, so it's not easy to put together a nice little system and get some information. So I've looked at a couple of simple continuum or field problems here. And the first is the thermal problem. We have a temperature, some boundary conditions, insulated, and another temperature. And we have heat flow, and of course we have a temperature distribution over all this. We'll let this be a two-dimensional problem. We have a temperature distribution all over this continuum. And it's difficult to find unless the geometry and boundary conditions are simple. And here we have charge distribution and some different mediums. And again, we have electric field. And again, it's hard to find the electric field unless we have some simple structure, simple geometry, and so forth. And down here, we have windings and magnetic flux, magnetic field. And again, unless things are simple, it's difficult to find the magnetic field. So what we should do then is look at this in terms of a systems modeling approach. And let's put some components in here and build up a network. And then we'll solve that. At least we'll find out temperatures and flows at certain finite locations, and that's what we're going to do. So the graph theoretic field model. Again, this is for spatial continuum, salient steps, and this is an interesting point here too. I want to point out this is what I call a direct discrete approach. We haven't started with any partial differential equations or any functionals. We're going to go right in and look at the physics and build a model. And then I'll show you later that our model is correct because in the limit we get your classical partial differential equations and functionals. So the secret is, and this is nothing new, but we did discretization of the spatial continuum according to an orthogonal coordinate system. And rectangular is the easiest. Some arbitrary ones are also possible. Identification of the so-called through and across variables of the specific field. Okay, I'll show you examples of that. Formation of the field graph based on steps A and B. And we pretty well know that it's going to be repetitious and routine, so that's not going to be too difficult. We just have to do it in a systematic way. Construction of constitutive equations. And this models the kind of the flows and nodal differences inside the, potential differences inside the continuum, and boundary conditions, and in terms of the through and across variables. Okay. And at the end here, we compilation of the interconnection equations from the field graph invoking the vertex and circuit postulates. Well, there we have it, the idea of, you can see the idea of components coming and the idea of the interconnection coming. So spatial discretization, and we do this in a special way. We have both some primal discretization and some dual. And so what we see here is a set of primal points in bold, and we can connect those by primal lines. And looking at 4 primal lines, we have a primal area, and give that some depth, we have a primal volume. The dual is kind of interlaced in between as primal points, and connecting the primal points, primal lines, and looking at region here, we get a dual line, and inside here we have a dual area, give it some thickness, and we have a dual volume. And we'll look at two-dimensional situations, so we'll give areas will be length times length of some of the lines times the thickness. It's a little easier to look at some of the limiting cases if we just stick with the rectangular structure. So here we have the primal points along one horizontal axis and also along the vertical axis, and the same for the dual information. You can see how it's a nice regular structure. And so here we have, say, a dual length, and here we have a primal length. Okay. Now, through and cross measurements, remember we go back to the basic idea that we need through is in series and the cross is in parallel. So looking at, what we'll do is start with the simplest. We'll look at some primal points, and this would be say the dual surface that sits halfway in between or partway into. What we'll do then is, there's the across measurement, terminal node, point to point. It's in parallel, and there's the through. It's in series with the points or terminals, and it's through in this case, through the dual area. And we can also look at and we'll see these measurements serve well. Look at modeling the constitutive properties. In terms of sources, we can look at a pair of primal points and talk about a flow into the dual volume, and there's the cross measurement in parallel with respect to the pair of points. Now the field graphs, again, if we look at what we have here, we have the primal points replaced by nodes, and there's a primal edge, your primal terminal graph, for example, and we can see another primal. And then in green we have the duals, and the duals are the nodes for the duals would be the dual points. And we would have a flow measurement across a primal surface, and across is measured with respect to the dual points. And we're a little careful though. We'll take the primal edge and we always turn it clockwise to get the dual. And as you can see, there's 2 rotated clockwise, 3 rotated clockwise, and then there's 4 rotated. So we'll keep that in mind, that there's a bit of a system to that. Important models, remember the 2 parts. There's the terminal graph and the terminal equation. So looking at what they call the constitutive property, we'll look at, let's say, 3 primal points, and there were the measurements. There's the terminal graph, and this measures, say, a through and a cross, a flow and a potential difference. And since the terminal graph has two edges, we need 2 equations. So there's, say, the pair of flows and a pair of potential differences. And this is how we build the constitutive coefficient. It's quite simple. There's the material property, there's the dual area, and it's divided by the length of the primal. And so what we have is kind of a bulk of taking the area over. We have an intensive variable, and taking the across, which is like a potential difference, and dividing that by L, we have kind of an approximation for the gradient. So it's quite simple but very elegant. And these terms here would come into play with asterisks in case we have some coupling in say an isotropic material. For the source model, there's our couple of point, dual volume. There's the terminal graph. In this case, we just specify the flow, for example, the volume times the density. Straightforward. And we built these models based on the primal graphs, but we can also do this for the dual graph as well. So interconnection equation. So here we see a little snapshot of the field, and again, we're just working in 2 dimensions. So here we have the terminal graphs for the constitutive properties 1, 2, 3, 03, and 4. And for example, there's the terminal graph for a source. And the vertex equation yields. So if we just do it, just do a little cut set. And incident towards is minus, incident away is positive, so we get minus y1, minus y2, plus y03, plus y04. And there's the source, minus y03 is 0. Simple. Now, in the other case here, there's the pair of across measurements, x1, x2, and let's introduce these ideas of these nodal variables, nodal cross variables, and we'll call them phi j, phi e, and phi f. And now we can see some simple circuits here, E, G, F, E, whereas E, G, F, E, and that translates into the simple equation here. We can pull out x1, And there we have, that's basically that idea, the nodal transformation equation. And the same for the circuit JE, and that'll finally give us x2 is equal to the nodal measurements phi j and difference with phi e. Application. So let's look at a few things. We'll do heat transfer, heat conduction. It's a scalar potential problem. What I want to show you is that how we can get from the graph theoretic field model the finite difference method, and then take it on, and we simply get the partial differential equation in the limit. And we'll also look at how we can view the finite element method from the graph theoretical field method. And in the limit, we get the functional. So the partial differential equations are this typical starting point for finite difference, and functionals are the typical starting point for the finite element. But we're direct discrete, so we can bypass that. And then we'll look at electric and magnetic fields, electrostatics and magnetostatics. So heat transfer, we'll do heat conduction. We'll do this in 2 dimensions, and what we see is through and across variables. These are well known. So the through is heat. Whoops, I'm sorry. Is a heat flux. You call it Q in watts, and temperature difference in degrees. And obviously, their product isn't power, because we already have power. So here we show the terminal graph for the constitutive properties 1, 2, 0, 3, and 4. And there's the heat flux measured across the dual area, temperature measured across between the primal nodes. That's straightforward. And here's a flow source coming in. The component equation is constitutive. It follows what we said. There's the heat flow, there's the temperature, there's the conductance, heat conductance constant, there's the area of the dual surface, and there's the length between primal points. For the source, we have a flow, which is the volume times, say, a density. Interconnection equations, we just back up. We can see that looking at the vertex postulate, or the nodal cut set equation at E, and we get quite simply plus Q3 plus Q04 minus Q1 minus Q2 minus Q2 is equal to 0. And for the circuit, E, F, E, G, H, so we're going around the circuit here, F, E, G, H, and we can see we're going to get T1 minus T2 minus T3 plus T4, and sure enough, that's what we get shown at the bottom here. Finite difference method. Okay, so let's just look at E, consider node E, and we'll start with the nodal cut set equation and substitute in the constitutive equations. And so Q1, there's the constitutive coefficient times T1, constitutive coefficient, so forth. And then we just move the heat source over to the right-hand side. Now, bringing in the nodal potentials, so T1 can be replaced by, T1 is replaced by EF, phi F minus phi E, and so forth. So there's the replacement for T03, there's the replacement for T2, and replacement for T04. And if we can simplify this by introducing uniform geometry. Delta x is delta y, and so these terms here cancel out. And this all simplifies down to a very simple term in terms of the nodal temperatures in this case. There's the conductance. We get 4 times the temperature at phi E minus temperature at F, E, and 1, and that's just equal to the source term on the right-hand side. We repeat this for all the nodes, and then we get simply a set of equations we can solve. So let's go to the Poisson's equation, which is going to be the limiting case of the nodal formulation. So if we start with this is the nodal formulation here. We've got it down into these nodal temperatures. Now, what we'll do is we'll let these differences become small, so we can see that if we introduce a potential function, then this any difference in delta phi is just using first order Taylor series. We get the partial derivative times a little bit of space here. So when we substitute this in and be a little careful, we get a difference in derivatives, and a difference in derivatives in both in the x direction and the y direction. And the geometry will take care of itself. We get a cancellation of delta x's, but when we introduce the Taylor series, we get another delta x back, and same over here for the y dimensions. And finally, in the limit, we get the partial differential equation with respect to the temperature, and this is simply Poisson's equation. Or in vector calculus, we get the divergence of the gradient is equal to minus the term on the right-hand side here. Didn't have to start with this. Okay, let's look at the, well, we're in thermal systems. Let's look at the finite element method. We've seen finite difference from graph-theoretic field model. Let's look at the elements. So here's how we think of this. There's the field as a continuum, and what we'll do is, the thinking is, let's break it up into elements. So these are these contiguous little areas here. Again, we'll think in 2 dimensions. Now, this element interconnects actually at an infinity of terminals, and that's not what we want to deal with. We want it down to a small number of terminals. So the simplest number of points or terminals of interconnection would be 4, and that would be at the corners. And so we have a component 1 here interconnecting with another component here, and then these all look the same. So let's look at the model for this from multi-terminal representation theory. So let's take the 4 points of interconnection. We'll call those terminals, and we'll also introduce a 4th terminal, which will be at the reference point, and we introduce that in case we have sources which will be referenced from the data here. So we have, what do we got? We got a 5-terminal component, 1 process. So for the terminal graph, we need these 4 edges, form a tree. Beautiful. Now we need the terminal equation, so we'll just look at just the constitutive relationship, and so we have the through measurements based upon the terminal graph here, and we want to relate that to the cross measurement. And what we'll do then is let's look at the G as being this product, this multiple product form here. So there's this A is topology, C is constitutive characteristics, and N is going to be this tough one, this relationship. So let's go into the element and put in the pieces of the graph theoretic field model. So here we have the spatial discretization, and the key here is I pushed in the dual points just so they'd be inside the surface, so they kind of kept all. So the element information is all kept together, and we do this all the way around here. Now we see dual lengths, which will be dual surfaces, primal, and on and on and on. And now looking at the terminal graph of the constitutive properties, there's the field graph. So there's the pair of complementary variables, say flow and temperature difference based upon information here. Now we can also look at the topology of our little field graph, and this gives the incident matrix. So there's the nodes and there's the edges, and we get the relationship. So that takes care of the matrix A. Okay, we're doing well, we're getting there. So let's go down to getting to the geometry. And there's this simple way to do this. If we go back, we can see that all elements are defined by a coordinate system alpha beta, which runs from minus 1 to plus 1. So it's like a little 2 by 2 region if you think of it in a rectangular region. So all elements will have this. So we can build these weights based upon whatever your alpha and beta has to be, 4 weights, and then we can use the global information u and v at the terminals of interconnection to give us what the coordinates of the primal and dual points are. And so there's the u, and there's the v, and then primal lengths and dual lengths are just related to the primal and dual points, so we can take care of that. We can take the conductance and then the geometry and build our constitutive coefficients for the 12 little constitutive components, and that builds a nice little matrix. So that takes care of the C matrix. Okay, we're doing really well. Now we need N. Now N is typically the tough one to get, but what we'll do is instead of solving out the interior, we consider an interpolation function. Say the temperature profile over the element will be fairly regular, fairly simple, fairly well, not known, but routine. So we use what they call an interpolation surface. It ensures the circuit postulate is satisfied along interconnecting surfaces, but we may err on the vertex postulate. So for our elements, we use the same weights that we use for the geometry. And for example here, we can find out that the temperature at B is related to temperature at A half, temperature at C half, and you can see that's pretty straightforward. So notice we've got this matrix N basically free. So now we can form the coefficient matrix G for our element or our multiterminal representation. And now what do? So we now have a model for the element. We interconnect the elements. It's like just interconnecting all those multiterminal representation, and we solve the problem with elements now. And functionals, what we can do is same thing as we did before, do a small region, and based upon the principle of orthogonality, the functional can be written as this matrix product. And I pulled left C by itself, and in more detail we find out that this guy here is just a difference in these temperature differences, and since this is the transpose, this column becomes a row. There's the matrix C, and putting this all together and taken to limit, we get our functional, which is this integral of derivatives, first order derivatives squared over the whole element. So it's now an area property. Looking at electrostatics, what we need is the primal graph, primal lengths, dual areas, and dual volumes. So I've taken a little snapshot again here. And the through and across variables are rather interesting. The across is straightforward. It's just the electromotive force in volts. And you more readily see this as related to the electric field and spatial length. The through is rather interesting. It turns out to be the polarization flux, and it has units of charge. And looking at it more in the electric field domain, so there's the polarization, and times dA, of course, dot dA gives us the flux. Now, suppose we have a problem where we have a line of charge coming out at us, so we get an electric field in just 2 dimensions, and we'll let this be a source, this charge here be a source. Then moving on, we get the constitutive equation is just the polarization flux times the permittivity of free space, and this is the dielectric constant. There's the area, length, and there's the cross variable. So it all falls into that pattern. And the source will just be a charge based upon some geometry and some density. Interconnection equations for the dual surface around E with charge QT, the vertex postulate, this should be just the sum of 6 for these 2-dimensional. And for the circuit, we can get the sum difference of the EMFs as shown. And we see that those vortex equation is just a discrete representation of Gauss's law for electricity. And so there's the Gaussian surface relationship. And for electric field from charge, the circuit equation just gives us the relationship for a circuit of electric field and displacement. So let's say we have a electric current coming vertical to the perpendicular to the screen, and we'll let this be the 2-dimensional field plane. What I'm going to do here, without explanation, is indicate that the through and across variables for the magnetic domain, or the magnetic flux in units of Webers, and the magnetomotive force in units of ampere turn. This H here is the magnetic field intensity. And the constitutive relationship again has the same form: flux, permeability, area, length, and the cross measurement. Now notice how what we're using is going to use the dual graph for the magnetic variables. So there's the flux and there's the magnetomotive force round and round. The trouble is it doesn't give us anything. It doesn't give me anything useful. So what I'm going to do, what we do, is let's use the dual of the dual, or it becomes the primal for the magnetic variable. So we'll keep the current in the primal domain. And now there's the dual for the magnetic variables for 1, and there's going to be the dual, which is the primal for 2, and et cetera, et cetera. So what happens? What happens when you go from dual to primal to dual is the relationship of the variables switch. So now flux, which was through in the dual, now becomes cross in the primal, and the EMF, which was cross in the dual, becomes through in the primal. Okay, now let's write the vertex equation at E then. So vertex equation at E is looking at this. There's VO3, it's positive. VO4 is away, it's positive. 1 and 2 are negative, and the current is in, so it's negative. So there we have the relationship of the magnetomotive force and the current. Now, if we just substitute the terminal equation so that we get the magnetomotive force becomes the magnetic field over the permeability, lo and behold, this is just a discrete version of Ampere's law. And for the circuit, EF, EGH, which is that F, E, J around here, we use the fluxes, which are the cross variables. So this is phi 1 minus phi 2 minus phi 3 plus phi 4. But really, these are fluxes into a closed region, and this is now just Gauss's law for the magnetic field, which is more clearly written in the form shown here. And finally, we get the magnetic vector potentials, the last thing I'll cover here. So what we have here is looking at nodes E, F, and G. So we just go back to E, and there is the original current, and this is just the complementary, we'll just call this the complementary flux, so that's the across. And looking at, and again here we have current complementary flux, current complementary flux. And this terminal graph here, its across measurement is actually phi y, because it was originally this direction. And this terminal graph here, its across measurement is the flux in the x direction. So considering the two circuits, G, F, E, and G, there is a G, F, E, and G, we get phi f plus phi y minus phi e. And for the other circuit, G, E, J, etc., we get phi e minus phi x minus phi j is equal to 0. Now replacing phi y with the magnetic field and an area, and replacing these complementary fluxes with a measurement, a new variable f, and the thickness of the field h, and doing a little bit of work here, we get that the magnetic field in the y direction is just minus delta change in the variable az over delta x, and doing a little work for bx, getting a sign right, we get bx is the change in the difference in the a variable over delta y. And in the limit, we get the sum of bx plus by, this relationship, this partial differential relationship, and lo and behold, that is just the b is the curl of a. And so the complementary fluxes are the counterpart to the magnetic vector potential. And I'm just in time here. We'll finish up with a couple of statements which I wanted to show, and that was that the graph theoretic field model is a discrete counterpart to classical spatial field theory. And it has shown the soundness of the principles of graph theoretic modeling in the sense that we've gone from the discrete model to classical models, and again looked at showing how that it relates to some of Maxwell's equations, and finally the graph theoretic field model provides a unifying perspective for the common numerical methods. And I think that was my greatest happiness, was to show the relationship between finite difference and finite element. And with that, I'll end, and thank you.
So the type of graphs you have shown are 2D lattices, possibly deformed, and I was wondering if you want to actually improve discretization over a certain region of your field. Is that possible? Does that bring additional challenges in terms of formulating this?
To go 3 dimensions?
Even in 2 dimensions, let's say if you want to take just a piece of your lattice and actually add other points in that region.
No, that's quite easy. And in fact, I would take that idea in terms of the functional, where you begin to refine your spatial structure until it becomes a continuum. Yeah. Thank you.